This is still section 11.7, events involving and conditional probability, part 2. It does have a lot of formulas in this section, is why I had to split it up into 2 different parts. The next formula is for when you see the phrase at least one inside a probability problem. You're going to take the number 1 and you're going to subtract the opposite probability from that, the probability of none. And for when we do the probability of none, that's going to involve timesing, multiplication. So I'm going to draw a little time symbol in blue below it. So for now, just think of whenever you see the phrase at least one, you're going to do 1 minus, and then you're going to multiply some fractions. Why 1? Why the number 1? And why are we subtracting? Well, it goes back to the fact that if you add up all of the possible scenarios in probability, it adds to 100%. The number 1 is the same as 1.0. And if I convert that decimal number to a percent, 1 is the same as 100%. So thinking of an example in our heads, and I'm going to use percentages because I think percentages make a little bit more sense than decimals with this scenario anyway. Let's say that I polled the class and I found out that 70% of the class owns no pets at home whatsoever. So none or no. So 70% of your class has no pets whatsoever at home. Knowing that information, now let's say that I asked you what percent of the class owns at least one pet at home. If you said 30%, you're absolutely correct, because you take the 100%, you subtract what you do know the opposite scenario, that 70% of the class owns no pets whatsoever, and that implies that 30% of the class would have at least one pet, so one or more, in other words, at home. If I said the same thing with chance of rain, if there's a 70% chance of no rain whatsoever, there's a 30% chance you are going to get some rain. So it is the same scenario. So that's why we're starting with the number 1, same as 100%, and we're subtracting the opposite scenario. So just keep that in the back of your mind as to why we're doing that. Looking at example 1, it says there are 8 cans of soda. We have 4 colas, 3 orange, and 1 cherry. 2 cans are selected without replacement. Find the probability that at least one of those sodas is a cola. I know since we're drawing 2 cans that there will be multiplication somewhere within the formula, but what trumps everything with the probability sentence is the phrase at least one. Before I begin, let's go ahead and draw a picture just so that in the long run I can visualize this scenario a little bit better. So we have 8 total cans of soda, and they say 4 of those are colas, and it says 3 are orange, and it says 1 is cherry. Is the layout. Okay, so now we have our picture. We want the probability at least 1 can of the 2 that I select is a cola. Equals, using our new formula, the right-hand side of the formula, we start with the number 1 and we subtract the opposite scenario, which is none, meaning no colas. So when I say the word none, you just simply insert the word no in front of what the question's asking about. So I bring down the number 1 and the minus sign. The probability of no colas, we said that's going to involve multiplication every time because we're drawing 2 or more, in this case 2 cans. It's without replacement, so the denominator will go down. I'll put den and a down arrow. I'm going to go ahead and draw 2 underlines with a multiplication symbol there. I'll put an equal symbol after. And we want these underlines to match the phrase above. So this is still no cola. No cola. No means anything but. So if I take away the 4 cans that are in fact colas, I have 3 orange plus 1 cherry, which means I have a total of 4 that are not colas. So 4 out of the 8 cans are anything but a cola. So you have a 4 out of 8 chance that the first can you grab is not a cola. You get what you want. We always assume with probability here, selecting multiple items. So after you get one of these 4 non-colas, you're down to 3. Your grand total goes from 8 down to 7. So you're going to count down with these types of fractions. That's honestly the hardest part, is just setting up the multiplication every time. Now I can just type this whole thing just like that from left to right into the graphing calculator to make the graphing calculator do the work from here. Typing it in, we start with the 1. Oh, gotta turn it on here first, clear the old stuff. 1 minus, then we had 4 divided by 8 times 3 divided by 7. What's nice is that this graphing calculator is programmed to do order of operations, so it knows to multiply before it subtracts. And then math button, enter, enter. Final answer, 11/14. I'm going to jot down 11/14 as the final answer. Now you might be saying, well, that was a lot of work. Honestly, once you get the hang of it, this is quicker than the other way we could calculate at least 1 cola. Because the other way would be, okay, first figure out if the first can we draw is a cola, then figure out the probability that the second can we draw is a cola, then third part, figure out the probability that both cans are cola, then add up all 3 of those probabilities together. So that would still give you the same right answer, but that would be a lot more time consuming. So that's why it's just easier to work backwards and do 1 minus the probability of no or none, that opposite event occurring. Let's look at one more example of using at least 1, that probability formula, just to make sure that we have it down. So example 2, a survey asked 47 people what type of insurance plan they had. The results showed that 22 had a managed care plan, 19 had traditional insurance, and 6 had no insurance. If 2 people from this survey are selected at random, what is the probability that at least 1 has a traditional insurance plan? So the key phrase that tells me which probability formula I need to use is, of course, at least 1. Because I'm drawing 2 people's names, there is going to be some multiplication inside the formula, but there's always multiplication at the end of the at least 1 formula anyway. So the probability of at least 1 of the 2 people's names having traditional insurance, I'll just write at least 1 traditional equals. I'm going to do 1 minus the probability of the opposite scenario, where you just insert the word no in front of what you're looking for. So no traditional insurance. Equals, I bring down the 1 and the minus symbol. I'm going to always do multiplication for the no part. So no traditional, I'll put no TRAD, just to abbreviate a little bit here. So no means anything but traditional. If I take away those that did have traditional, I see that 22 had the managed care plan, plus I see 6 had no insurance. So 22 plus 6 gives me 28 people that had anything but traditional insurance. So 28 did not have traditional. So 28 names did not have traditional insurance. There were 47 people to begin. We always count down with these fractions because even if the question does not specify, these at least one problems will be without replacement. Without replacement means the denominator goes down. So we scoop up one of the 28. We're down to 27 that do not have traditional insurance. The 47 total is down to 46. So just type the whole thing into the calculator just like this. 1 minus 28 over 47 times 27 over 46. Math button, enter, enter. And if you've done it correctly, you should be getting 703 divided by 1081 as your simplified final answer. The last formula in this chapter for probability is called conditional probability. They're not being super creative with the name conditional because you literally will have a condition, something that's guaranteed to happen. Now find the probability based on what's guaranteed to happen. Whatever's guaranteed to happen, you're going to see the words given or given that. So be on the lookout. I'll put it in quotes for the word given, or they could even say on the homework, if you know that. So if you see the word given or if you know that, that's your cue. You're dealing with conditional probability. So the probability of some event, I call it E2. And I read that one vertical bar as given. Given, in other words, if I'm guaranteed that event 1, E1, is going to happen, equals. First, you're going to take the number in the intersection of event 2 and event 1. So little n, a lowercase n, the number in event 2 and event 1, and you're going to divide that by what you know is going to happen, what you're given. So that's the number in event 1. This is the textbook official formula for conditional probability, the number in the overlap divided by the number in what you're given. However, you really don't have to memorize this formula if you understand what conditional probability means. So let me show you how I would figure out the correct answer without really having to use this formula, looking at example 3. Example 3 says a single card is selected from a deck of cards. Determine the probability it is a queen given that it is red. So there's our key phrase, given, or key word rather, given, that tells me this is conditional probability. So I'm looking for the probability of getting a queen card. The way that I notation-wise have the word given is using that vertical bar. So I draw one vertical bar, given that it is a red card. Probability usually means a fraction answer, at least to begin. So I'm going to draw a fraction bar. So I read this out loud. The probability of drawing a queen, given that you have a red card. With conditional probability, This is the only time I do not put the grand total in the denominator. So this is my only exception to that probability rule. Why not? Well, I'm going to work backwards every time I have conditional probability to explain why. So if I'm working backwards, after the phrase given that tells me what I'm guaranteed. So I'm guaranteed, in this case, red cards. So if I'm only given the red cards from a deck of cards, I do not have all 52 cards in front of me. Because what this question means is somebody has only given to you all the red cards. Now that you only have red cards in front of you, how many of those remaining red cards are also queens? You have 26 total red cards in a deck of cards. So you just have 26 cards, half the deck sitting in front of you. Of those 26, how many of those 26 red cards are also queens? Well, that would be the Queen of Hearts and the Queen of Diamonds. You're not going to have the Queen of Clubs or Queen of Spades if you only have red cards sitting in front of you. So that means you have two that are queen cards and also red cards. So I get 2 over 26. You can see how it does follow the pattern of the formula. What you're given goes in the denominator. We were given red cards. The overlap, the word and, between the two events is the numerator. Queen and red, well, there are two cards that are both queen and red. I'm going to always do the denominator first, which is what comes at the end of the sentence. And then the overlap between two events will always be in the numerator. So 2 over 26, which will reduce down to 1/13. 1/13 is the final answer for example 3. Example 4 says the table shows the number of college students who prefer a given pizza topping. We have freshmen, sophomores, juniors, and seniors who are polled. They like cheese only, meat toppings, and veggie topping pizzas. Before I go any further, whenever I'm given a table, I always check to see if I'm given the totals. And thankfully I am. So I have the totals of all the rows, and I have the totals of all the columns. If I did not have those totals for any table in this chapter, I would need to take an extra minute or two and add every row and column up myself. On the bottom right corner is going to be the grand total every time. So 224 total people were surveyed. Part A, determine the probability a student prefers meat toppings given that student is a junior, round to the nearest thousandth. The key phrase that tells me the formula to use is given that. So going in the same order as the sentence, we want the probability the student prefers meat toppings. So I'll write meat. Given that, one vertical bar, the student is a junior. I'm going to draw a fraction bar for my setup. As soon as I see that phrase, given that, I always work backwards. So I'm going to figure out the denominator first. This question means if you're only given the juniors, now how many prefer meat toppings? What's the probability of selecting someone who likes meat toppings if you're only given the junior names from this study? So if I'm only given the junior names, goodbye to all of the other columns. I only care about this column right here. The total of that column is 64. So there are 64 total juniors. Of those 64, how many of those juniors are also meat topping lovers? Looking up the meat row right here. 15 of the 64 juniors prefer meat toppings. So I'll just write meat and juniors. If you are looking at the formula on the previous slide, I don't even bother with the formula. I just look at what I'm given at the end of the sentence, and that's the row or column in that whole table I focus on for the entire question. I was given juniors for part A, so I only focused on the junior column for that whole part A question. Now we're going to type it into our calculator. We're going to round to the nearest thousandth for a change, which is 3 digits to the right. Let me erase some of my scribbling so this is easier to read here in the long run. So I'm going to type in 15 over 64. As I type in 15 divided by 64, resist the urge to math enter, because it actually wants the decimal for a change. We said the thousandth place is 3 digits out. We only care about the digit after that dictates if I round up or round down. So the digit after that is a 3, which means we round down. In other words, keep the third digit the same. So that's approximately 0.234. I'm going to go ahead and write that down. So approximately wave 0.234. If you want to go ahead and put the 0 in the whole number spot, you can, just to emphasize the location of the decimal point. Let's try one more using the same exact table. Part B, determine the probability a student prefers veggie toppings given that student is a junior or senior. Round to the nearest thousandth again. So we're looking for the veggie lovers given that we have a junior or a senior. All right, equals. I'm going to draw my fraction bar. We always work backwards with conditional probability whenever you see the phrase given that. So if I work backwards, I only care about at the end of the sentence, we're guaranteed just the junior or senior names. So freshmen, sophomores, sorry, we don't care about you here. Get rid of the totals over here. So I only care about the juniors and the seniors. We have 64 total juniors plus 52 total seniors. If I do 64 plus 52, we only have 116 total people in the junior and senior columns. Still focusing on just those two columns for the entire question. Whatever you're given, whatever you're guaranteed, that's all you care about for the entire question, keep in mind. So of those juniors and seniors, how many liked veggie toppings? Well, 28 juniors liked veggie toppings, plus 18 seniors liked veggie toppings. I know that's supposed to be an 18. It's kind of hard to see my 1 there with my messy handwriting, but it is an 18, I promise. So 28 plus the 18 gives me 46. So 46 junior veggie lovers and senior veggie topping lovers divided by 116 juniors and seniors. Go ahead and round 3 digits out. Try it. You should be getting approximately 0.397 if you have done it correctly on the calculator. I got that answer because when I type in 46 divided by 116 and I hit enter, if I'm rounding 3 digits out, I look at the 4th digit. It's a 5 this time, which tells me to round up. So the 6 will round up to 7. So that's approximately 0.397. 0.397, final answer.